All right, continuing on with the analysis of variance. Just to remind you, SSC, MSC, RMSC are quantities that will continue to be representing what they did represent before in simple linear regression. So actually, SSC is the sum of the residuals squared. So what that means is that you take the actual minus the predicted value and then square that and sum of those, all of those. So that's the sum of the squared errors. The only difference is that y hat now is a combination of more than one predictor. So we have a slope for every single variable. So if we have k, we would actually have k slopes. So the slopes would be from 1 to k, and then plus the y-intercept. The estimator for the variance around the regression line with k independent variable, the only thing that changes is that, and again, these estimators MSC, and again, some software actually call it s squared or s of squared of y given x. All of that is representing the same quantity. So that's actually SSC divided by n, the number of observations, minus the number of estimated parameters. Estimated parameters is, well, in this case, we have estimations for the y-intercept. We have estimation for the slope of variable 1, variable 2, up to variable k. So in other words, we can just say that is n minus number of slopes plus 1. So that would be n minus k plus 1. We call these the degrees of freedom. And those are the degrees of freedom of the unexplained variability. There's also other degrees of freedom that we will refer to. Specifically, there's something else called the model degrees of freedom. So I'll explain that now in terms of the explained and unexplained variation. In every regression, we have what we call the total variation, SST. SST is measuring how away is each observation from the average of y. So SST actually just takes into account the y variable. It doesn't use any predictors at all. So if you see this green, this is y bar, this is the average y, then the way the SST is calculated is by summing the actual values minus the mean of y and squaring that. So really, it doesn't take into account anything related to a predictor. It's just taking every point, let's suppose that this is a point up here, and just measuring how away it is from the average. So that's what you have here in SST. That's the total variation. Ideally, if we have a predictor variable, we want to measure the unexplained variation. What that means is, if the predictor is good, then you would assume that the unexplained variation would be less than, of course, the total variation. The way that this is calculated is taking the sum of the actual minus the predicted value squared. Now, take into account that this predicted value contains all of the parameter estimates. And what that means is that what we are taking is the slope, and we're taking how away is the point, yi, from the predicted value, y hat. So SSE is just that difference now. Difference from the point, the actual value, to the line of prediction, or to the plane if it is more than one predictor. But we also have an average unexplained variation. In the average, whenever we take an average, is the sum of the squared errors and dividing it by n. But in this case, we are dividing by n minus k plus 1 so that we get this estimator to be what we call unbiased. Unbiased is that the mean of that estimator is the true value that we want to predict. That is about the unexplained variation. there's also an explained variation. And what we refer to that is what is explained by the model. And we call that SSR. SSR is the difference from the, we have SSC, we have SST, which is the total. So if we see here, SST is just a difference from the actual value to the mean, and SSC is the difference from the actual value to the prediction, y hat. But then the SSR is just the difference from the prediction, y hat minus y bar, which is the average squared. So it's that tiny thing down there. In this case, SSR is lower than SSC, so the unexplained error is greater than the explained. And that's not what we want in the model. We want SSR to be larger, the explained variation to be larger. The average explained variation is dividing SSR by K. K is what we call the model degrees of freedom. Okay? The model degrees of freedom is different than the degrees of freedom for the unexplained variation. The model degrees of freedom, every variable contributes something to the model degrees of freedom. So for instance, a numeric variable, let's say the variable age, contributes 1 degree of freedom. If we have a variable such as the number of bits of bidders, that also contributes 1 degree of freedom to the model. As long as the variable is numeric, it just contributes 1 degree of freedom to the model, because that would be the number k is just the number of predictors. Now, there is a tiny difference from the degrees of freedom that we will see later on, and that is when we have categorical variables. So let's say that we are talking about a variable, let's say a type of clock, and that type of clock is, let's say, type A, type B, and type C. That variable is no longer a numeric variable, it's a categorical variable. But that variable actually doesn't have 1 degree of freedom. It actually has the number of classes minus 1. So in this case, this variable contributes 2 degrees of freedom as opposed to 1. We'll see more on that later on, but for now, when we ask how many degrees of freedom are contributed to the model degrees of freedom for these variables, if they are numeric, they contribute 1 degree of freedom. Okay, and the next part that we will see later down the road has to do with how the models get more complex as the number of degrees of freedom actually increases. So we'll stop it there, and then we'll continue later on.